Good morning, everybody. Thank you very much for attending today's webinar on 10 things you can do with the pump junction. My name is Ben Kieser, and I'm with Applied Flow Technology, and there are a lot of really cool things that you can do with our software, and I'm going to be focusing on just one specific component today, mainly with AFT Fathom, and you're going to be able to take a lot away from it, and so I'm excited to go over these capabilities with you. The webinar is being recorded this morning, and that way afterwards you'll be sent a link either later this week or early next week. That way you can watch the recorded version of the webinar. You can also send it around to your colleagues. That way they would be able to watch it as well. I want to make note that my presentation is not available with the webinar link that you'll get, but I don't really have that much going on in the slides anyway, so everything's going to be demonstrated in the software today. So I'm going to go ahead and get started. If you've never worked with our software before, what I like most about it is that it's incredibly user-friendly, easy to learn, easy to teach it to somebody else, and it's also very easy to review other people's models. And that's because of the standard format that the software is built in. And so you're able to get a lot more done in less time. We have a lot of ways that you can quickly scan down your model and check for potential typos or unit mistakes, and so that will help you prevent a lot of mistakes and rework. It also makes it very easy to explain what you're doing in your system to non-fluids experts. And so that's a key capability that's available for you. And then finally, it helps you get the right answers faster. And with all those things combined, it makes everybody happy. So different things that you can do with our software. Yeah, sizing applications, you can size anything like pumps, valves, heat exchangers, orifice plates. I'm going to show you how to size a pump today, and that's just part of the presentation this morning for the 10 things that you can do with the pump junction. You can easily understand how your flow demand and pressure supply is changing throughout your system. You can do a design feasibility analysis, and so our software will show you if your design will actually work or not. You can easily model different operating cases within a single model file. And that's done with our Scenario Manager, which is one of the most powerful features of the software. You can model any variety of cases that you want within a single model and change any parameter that you like. You're not limited to just changing boundary conditions or turning things on and off. You can change any input parameter. And there's intelligence built in so that if you make a change at a parent scenario, it will pass those changes down to the child scenarios, so you only need to make the change once. So lots of efficiency is built into the software. You can easily model different system configurations very quickly. You can do a full heat transfer analysis. You can do transient analysis. With pumps, you can model your pumps changing their operation over time, either with changes in speed or changes in their flow set points. There's a lot of flexibility available to you there. You can model your system performance and make sure that you're operating close to your best efficiency points. You can things that are important for you to do with the system model is to calibrate it to measure results, account for any leaks that might be in your system, account for scaling and fouling that might be built up. You can also account for pump and system degradation. I'm going to show you a form of this today, which is not really degradation, but if you're pumping a very viscous fluid, it's really important to account for the correction factors where your pump will have to work harder to pump that viscous fluid. And so you'll see how we do that later today. You can also quantify your energy consumption, maintain code compliance. We have a design alert manager, which you can set up maximum or minimum values for pressures or flow rates or velocities for pipes and junctions in your system, and that's how you can easily stay within your code compliance. You can do a cost analysis of your entire system. Water hammer analysis is available, and slurry modeling. So those are a lot of different applications that you can work with in our software. What they'll do for you, they'll help you ensure a safe and reliable operation. You'll be able to maintain code compliance, see how system modifications will impact operation. One thing that's really important is that it will increase the lifespan of your piping system equipment. And so I very often hear stories where people commonly tell me that they're always having to replace, their seals on a pump, for example. And it's not because the seal is bad. It's because the pumps are not being operated properly, and they're operating way far away from their best efficiency point. That causes a lot of vibrational problems, and the seals fail. So it's not that the seals are not quality, it's the pump killed the seal. So that's something that you're able to do with our software. You can improve your pipe flow analysis efficiency, reduce energy consumption, and increase your energy cost savings. There's a couple examples. One of our products saved $100 million on a seawater pipeline in Saudi Aramco simply by changing the wall thickness in the right configuration. And then AFT Fathom was able to save the Chrysler Automobiles plant in Michigan $194,000 a year in energy costs. And so I'm going to show an example of what that would look like later today. All right, I'm just going to go ahead and skip past the majority of these bullet points. A few important ones is we have built over 100 verification cases for our software. We have built models of different published examples, and we have compared the results to show that the calculations are accurate. We've also had an entire nuclear verification and validation done with all of our software products by a third party, and they went and evaluated the whole software to make sure that the calculations are correct, and that way each of our products can be used in safety related systems in the nuclear industry. You can very easily customize your own fluids, components, pipe materials. I'm going to get into how you can develop a custom component today with the pump junction. And so you'll see how easy that is. And then lots of useful reporting features are built in to easily present your results to your team and your clients. These are the different applications that our products are applicable for. Basically, my question to people when they ask if they would be able to use our software is, do you have pipes? And if you have pipes, then our software is going to be able to handle those applications really well. Our primary products are AFT Fathom, AFT Aero, and AFT Impulse. Fathom models incompressible flow for liquid piping systems. AFT Aero models compressible flow for gas piping systems. And AFT Impulse models water hammer for and surge for liquid piping systems. Each product has a number of add-on modules. Stay tuned for our webinars coming up in 2018. We're going to be doing a lot more webinars on the modules and AFT Aero and whatnot. And then we have a couple of products here, Mercury and Titan, which are really useful for design applications. They will automatically size pipes in your system in order to help you minimize your piping weight or your life cycle costs or your first costs, all while staying within your various design constraints. So those are really powerful tools that you'll want to check out when you have a chance. All right, so here's what we're going to talk about today. I'm going to go over a quick pump sizing example and how you size a pump, talk about how you would be able to model VFDs and do impeller modifications. I'm going to show a really unique capability where you can easily model a whole multitude of pumps and pump curves within a single pump junction, and that'll be a huge time saver for you. I'm going to talk about the end of curve flow rates, reference densities, viscosity corrections, how you can easily model pumps in series or parallel with one pump junction, and then I'm going to do an energy cost calculation comparison where if you use a VFD, it'll help save a lot of money in comparison to using flow control valves. So with that, I'm going to go ahead and get started, and I'm going to move my presentation over to another screen. I'm going to bring up AFT Fathom here. And so I've just opened the model, and I'm going to build the model from scratch, and that way you can see a high-level process of how quick and easy it is to do. I'm not going to spend a lot of time on each individual step, but you'll see how quick the process is. So when you first open the software, what do you do next? Well, if you click on the red status light down here, red means stop and green means go. So when I click on the status light, it brings up our checklist of items that need to be completed before you can run your model. And so I'm going to go through and start completing those checklist items. And the first thing is specify solution control. That's your tolerances that'll dictate if you have a converged solution. Our tolerances are tight and robust, and so they will solve 90% of your cases. And you're not going to have to fiddle around with that much. So that's why that item is already completed for you. The next thing is to specify system properties, and that's your fluid information. There's a lot of different pieces of fluid data that you can model. I'm going to use AFT standard with water at 1 atmosphere, and the temperature is going to be 70 degrees Fahrenheit. Calculate properties, and there we go. So my fluid properties are now fully defined for my entire system. Next, I'm going to build my model, and it's just going to be very simple. I've got a reservoir, a pump, and a discharge reservoir. And so I'm going to draw my pipes and connect the pieces here. And I'm going to make my text size larger so that you can see it easier. Your user options window is where you can customize all of your preferences. Now, if I click on the Define All Pipes and Junctions link here, it's going to do two things. One, it turns on our light bulb here, and it's going to highlight any label for a junction or a pipe in red that's not fully defined. And so that's a good visual indicator for objects that are missing information. Also, we have a list here where you've got all your undefined pipes and all your undefined junctions. And if you click on any of those, it will actually tell you which pieces of information are missing. So for my pipes, I need length, diameter, and friction model. For reservoir, I need a pipe depth and liquid surface elevation, etc. So this is a really good way if you have a very large model, you can quickly figure out what pieces of information might be missing. So I'm going to click on Close, and I'm going to start with my reservoir junction. This is going to be at a 10-foot liquid surface level, and my pipe elevation is going to be at the bottom of the tank there. And that's all there is to it. My discharge reservoir is at a 200-foot elevation, so I'm pumping water up a hill over a 200-foot elevation change. And my pipe is going to be connected at the bottom of that tank. Next, for my pump right here, I need to specify an elevation, and so it's going to be at 0 feet. I could enter a pump curve at this time where you specify your flow versus head, but I don't know my pump curve yet. I need to figure out which pump curve I need to be able to use. So in order to do that, I'm going to size my pump by using the fixed volumetric flow rate option. So with that, my design flow is 500 gallons per minute. I'm going to shoot for a 75% efficient pump. So when I click OK, my pump is now fully defined. After that, I just need to specify my pipes. All you need is inner diameter, length, and friction model. And if you do user specified, you can do absolute roughness or relative roughness, Hazen-Williams, explosive friction factor. There's a lot of friction models available for you to be able to work with. I'm going to choose from our pipe material database and choose steel pipe, and this is going to start off with 4 inches in diameter. In addition to not knowing what pump I need to use, I also don't know what pipe size I need. My requirement is that the velocity inside my pipes have to be less than 6 feet per second. And so I'm going to start off with a guess of 4 inches in diameter, and then you'll see how I can easily change the diameters to figure out which pipe size I ultimately need. This pipe here is 10 feet long, and one other thing I want to do is I want to display the nominal size on the workspace. There we go. Second pipe, this pipe is going to be the same diameter, 4 inches, but it's going to be 1,000 feet long. Couple of quick tips. In reality, this pipe could be traveling over a whole different change in elevation. And so if you don't want to model all of the different elevations with junctions, you can actually combine all the elevations inside the pipe if you want. So you go to the optional tab, check the box to use intermediate pipe elevations, specify how many intermediate points you want, and then you would simply type in the point-to-point length versus the end elevation. And that's how you can easily account for different elevations throughout a single pipe. You can copy and paste data if you already have that information in a spreadsheet, or you could import it from a CSV file. So that's a really convenient option that you can use if you want to account for elevation changes. The other thing is that in this pipe, I have a whole bunch of fittings and losses, and so you could have elbows. Maybe there's 3 of those. There's 5 of these. Maybe you've got some valves in there. Whatever. If you click on any of these rows, it's going to show you a picture of what that type of fitting looks like. And if you double-click the picture, it'll tell you what reference we're using for that loss model. So when you go in and specify the quantity for these fittings, we're going to total up the K factor and lump that K factor right into the pipe for you. So this is a really effective way of maintaining a highly accurate model, lumping in the fittings and losses into your pipe without having to draw them as actual junctions on your workspace. Now what I'm going to do, I'm not going to do it that way. I'm just going to go in here and type a constant K factor of 25. So that's going to be my K factor for the system, or for that pipe. Okay, now I do have 3 green check marks and a green status light, so I could run my model and get results right now. But there's a couple of things that I want to do first. What I want to do is I want to take this system and I'm going to duplicate it twice because I need to figure out what pipe size I need. So this is going to be a 5-inch system, and this is going to be a 6-inch diameter system. So in order to change that really easily, I can do a global pipe edit. Rather than having to go into each individual pipe and junction, I just check them off the list, and these are going to be 5 inches in diameter, and I'm only going to check the box to change the nominal size, and then I'm going to do the last 2, and these are going to be 6 inches in diameter. There we go. And then the next thing I'm going to do is I'm going to create a design alert. I want to make sure that I can quickly flag my attention to any velocities that are above my 6 foot per second minimum. So I'm going to type in 6 feet per second max velocity. You can type in whatever name you want. I'm going to choose velocity as the parameter. Maximum value is 6 feet per second. I'm going to apply it to all my pipes here. And there we go. So you'll see the impact on the results that this will have. Well, it's not going to impact the results. I'm just going to flag my attention to results that I want to quickly spot. I'm going to customize my output a little bit here. I'm going to add the nominal size to my list of output parameters, move it all the way up to the top, move velocity right underneath. I'm going to get rid of a few other pieces of information I don't really care about, and there we go. So now when I go to run my model, it's going to make me save. I'm going to call it pump sizing for webinar. And now I can take a look at the results. All right, so here we do have some design alert violations. These red warnings are telling me that my design alert has been exceeded for several different pipes. And as you can see here, the 4-inch and 5-inch diameter systems do not cut it. They're exceeding my 6 feet per second maximum, so I can't use those pipe sizes the pipe size I'm going to go with is 6 inches in diameter. So if I look at my pump operation, you can see how the pump head changes as you increase diameter. And so the bottom pump is going to be the one I'm going to work with, and the power draws about 37 horsepower based upon a 75% efficiency pump. So now I'm going to select a pump that's going to meet that operating point. In order to do that, I'm going to create a child scenario and call it pump sizing. So with my pump sizing scenario, this is where I can model different operating cases. And since I know that the 4 and 5 inch diameter systems are not going to work, I'm going to just delete those from the workspace. And I'm only going to have to focus on this single system. So when I go and rerun the model, I get the exact same results that I had before. But what I want to do is click on this button right here, the Suggest a Pump. And so when I circle this right here, it's that guy. That will help me select a pump that will meet my operating conditions. So when I go to do that, I click the pump with a spark, and I'm going to use the internet with IntelliQuip to search for a manufacturer that has a pump that will meet those needs. So I click on search, and these are the list of vendors that make their pump catalogs on their website available publicly for free. IntelliQuip works with about 30 different pump vendors, and if you subscribe to their pump vendors, then you can easily add those manufacturers to this list, and you type in your login credentials and whatnot. And so to keep things simple, I'm just going to choose the top one here, and I'm going to open a web browser, and this is where it'll take you through the process of finding a pump that will meet your needs. So I'm going to go next, and then I'm just going to choose the top product line because it's the easiest. Next, I'm going to choose the pump that's operating very closely to the BEP. So I'm going to go with the second pump in the row right here. And you can download all of this spec sheet information as a PDF if you want, but ultimately what you need is you need to get these pump curves into the software. And so to do that, you click on download, and it's going to download this IQX file. And I believe I already have that on my workspace or my desktop. I'm just moving it over so I can find it easily. All right. So now once I've downloaded it, I go back into Fathom, and I move on to step number 2 to open that downloaded file. And so this is the one that I'm going to use. Click Open, and then I'm going to apply that pump data to my pump. You could save the pump for later. If you want to use it in other models, you can. I'm not going to do that in this step. I'm just going to apply that to my pump in the model here. So now, if I open up my pump here, I have some additional pieces of information now. I have imported all of that curve data right into my pump model. So that's a really nice feature to really quickly bring in your pump data. So now I've got my head curve, my MPSH curve, and my efficiency curve, and all that's based upon a 2633 RPM pump with a 10.4 inch impeller size. So now when I go to rerun my pump or my model here, I can then compare results to my original pump sizing case to my pump curve case, and what you're going to see based upon the operation is that your pump curve does a fabulous job of meeting your initial operating point for your pump sizing case. So that's all it is. All there is to it to going through and sizing a pump. You've got your overall efficiency, what your horsepower is. I'm operating very close to the BEP, which is good, and I've got plenty of MPSH available, so I'm not going to cavitate through that pump. So that's all there is to sizing a pump here. Let's talk about a couple other things. If I go back into the pump, let's say that you know for a fact that there's no possible way for your pump to operate past 600 gallons per minute. And so if you have a system where you've done some sort of a change which results in a really high pump flow rate, and you know that there's no way for your pump to deliver that flow for you, what you need to do is enter a end of curve flow rate, because mathematically Fathom can still calculate where that pump is going to operate even if it's at a very high flow rate that's not realistic. So in order to do that, what you would do is go to the enter curve data window, and then on the configuration data tab you would click on this option right here to do a end of curve flow rate. So if you cannot operate higher than 600 gallons per minute, you type that in. Fathom would still find that you might operate past that value, but it'll clearly warn you in the output that you're operating past that maximum. And so that's what you would do for helping yourself figure out if you're operating at too high of a flow rate. So that's what the end of curve flow rate is. Next, let's go ahead and talk about impeller modifications. So I'm going to create another child scenario for that. Impeller modification. And I'm going to go into my pump. You can do it in two ways. One way, which is the simplest, is you can just simply ratio your impeller trim as a percentage. So if it's 80%, those are the two curves. You've got your original curve on top, and then the new curve, which is modified via the affinity laws. If you have the drop-down menus and the information here for your RPM and your impeller trim, you can modify the impeller in a different fashion. You can modify the impeller in an actual impeller size, so maybe it's 9.25 inches. That's how you can modify the impeller. So if I do that and click OK, I can run my model, and you can add this new scenario to your output. That way you can compare the results, and I'm going to add on a new parameter for my pumps, which is impeller information. So if I go to my pump summary tab, I can see that when I modify the impeller and reduce it down to 9 1/4 inch, it drops my flow down to 250 gallons per minute. So if you need to get lower flow where your original design flow is way too high, then you can trim the impeller in that fashion, and you can see how it's operating in comparison to the original cases. And then there's a new parameter that you can add. Well, not new, it's been there for a long time, but new for our webinar today. And it's this impeller information column. And so you can add in this value. That way it'll tell you what your actual impeller trim is, so you can see how things have changed in the different scenarios. That's all there is to it for impeller modifications. Next, let's talk about modeling the VFD. So I'm going to go back into the original pump sizing scenario, and I'm going to create a child called VFD. And so in order to do that, you would go to the variable speed tab, and you can do a VFD in two different ways. One is by typing in the fixed speed directly, and you'll see how we show both curves there. The other way is, instead of doing a fixed speed, you can do a controlled pump set point. So maybe I don't need my pump to operate at 500 gallons per minute. Maybe I only need 350 GPM for a off-peak operating case. So I've got 350 gallons per minute for my control set point, and when I click OK, I can run my model, and we'll add this onto my list of scenarios to compare the results. And voila. So this pump right here, my 350 gallon per minute pump, in order to get there, my pump has to drop by about 8% speed. So this will tell you what speed your pump has to drop down in order to help you achieve your desired flow rate. And this is much better than using a flow control valve, because you're not going to waste as much energy. So with this, you're still operating pretty close to the BEP. If you were to use the flow control valve, it's going to be wasting a lot more energy, and you'll see an example on that shortly. So that's VFD modeling. All right. So where are we at with our agenda here? Let's see. So we've talked about pump sizing, and we talked about how you can model VFDs and impeller configurations. We talked about end-of-curve flow rates, and so we've done a lot so far. Let me touch on reference densities really quick. In my model here, I am modeling water in this particular case. Now, for the most part, whenever you get a pump curve from a manufacturer, their test fluid is typically going to be water. Now, you're potentially going to ask, do I need to account for different densities when I'm pumping molasses for my pump versus when they test it with water? Well, the answer to that question is if they give you your head and flow curve in terms of head and volumetric flow rate, those two parameters do not depend upon the density. So when you do volumetric flow rate and head rise, then that will apply to any density that you're going to be pumping. However, let's say that you are given your pump curve in terms of mass flow rate, or maybe you're giving your pump curve in terms of pressure. In those cases where you're giving your pump in terms of either mass or pressure, there's this reference density section at the bottom of the window that appears right here. And so for mass and pressure, either of those parameters do depend on the density. So if you're pumping a system fluid which has a different density than the test fluid, then you do have to account for density differences if it's given in either terms of mass or pressure. Now there's a couple ways to do that. The simple way is if your test fluid is simply water at standard temperature and pressure, just click that option, and that's what Fathom will use to correct your pump curve. Or you can do a user-specified density, and so let's say that your pump was tested with molten sulfur for whatever reason. You can enter the density for molten sulfur, and then Fathom will correct your curves based upon density differences in that fashion. So this will take care of density differences for you, so that way you don't have to do it. Moral of the story is enter your pump curves in terms of either volumetric flow rate or head, or volumetric flow rate and head, and you don't have to account for density differences. However, if you enter a power curve instead of an efficiency curve, power curves also depend on density. So if you choose power for your power curve, then you'll have to account for reference densities there as well. So be aware of that when you're dealing with your system fluid. All right. So that's another one bites the dust off our list here. All right, I'm going to talk about modeling pumps in series and parallel right now. And if you want to model a pump in series or parallel with, you can do that in a couple different ways. So let me create a new scenario here. Pumps in parallel. One way that you can do it is actually graphically. And so what I can do here is I can split my pump or my pipe just like this. Spread this out a little bit here. This is going to be at 0 feet. That's at 0 feet. This is going to be 10 feet. I'm not going to do my losses on this pipe. That pipe is going to be 1,000 feet. When you use the split pipe feature, it's very useful, but it will split your pipes directly in half. And so if they are, if that's not what they're actually supposed to be, then make sure you go back in and update your pipe lengths accordingly. All right. So this is one way where you can easily model your pumps in parallel. I can just create my system, and if my suction and discharge piping is exactly the same, just duplicate it from what it was before, and that'll save you a lot of time and effort. So now I have an identical copy of the suction and discharge pipes. I don't have to go in there and re-specify them. I don't have to go in and specify my pump because it's got all that information there already. So this is one way that you can model your pumps in parallel. You could do the same idea if you're modeling them in series, but when I go to run my model here, it'll converge, and let's just focus on this one scenario for right now. I'm not going to compare it to my other ones. So when I put pumps in parallel, I'm now getting 348 gallons per minute times 2 through my system. So if I right-click and hold on the discharge pipe, I'm getting about 700 gallons per minute through my system right here, and that's when you model pumps in parallel. So as you can see, my original design case with my original pump curve was 500 gallons per minute. If you have a very system with a lot of friction in it, or when you're trying to get a lot more flow, just because you put another pump in parallel does not mean that you're going to actually double your flow rate. And so it's going to be less. And as you add more and more pumps, you get less and less amounts of additional flow. This is one way that you can do it, and that's where you would model the actual suction and discharge piping on your pump. There is a simpler way where instead of modeling the actual suction and discharge pipe with a additional pump, you can go back to the original one, and on the optional tab, choose parallel for number of pumps at that location. And I'm going to put in 2. And so now when I rerun the model here, it's going to run both of those 2 systems simultaneously with each other. And I'm going to add one other parameter for number of pumps. So as you can see in the pump summary, my system on the left, it's got 1 pump for each of them. And then for the system on the right, I'm going to move this to the side here. The system on the right, it uses 2 pumps in parallel, and you've essentially got the same flow rate, 698 gallons per minute versus 695. And so the way that you can do this effectively is if your suction and discharge piping is very, very similar and your pumps are exactly the same. Same pump curve, same pump model, same lot number if possible, then that's how you can easily model pumps in parallel or series in that fashion. You want to make sure your pumps are exactly the same and not different pumps or different models, because then they could potentially fight each other, and that can cause some pretty big issues. Just for fun, let's go ahead and take this system, and for the pump, let's do 3 pumps in parallel and see how much more flow we get. So I'm going to bump that up to 3 pumps, and my previous flow rate with 2 pumps in parallel was 700 gallons per minute. My new flow rate with 3 pumps in parallel, 750. So this just goes to show you, as you add more and more pumps in parallel, you're not going to get that much additional flow. You could show this with a system curve, and based upon the steepness of your system curve, that would show you where the point of diminishing return is going to be. I'm not going to spend much time on that right now. All right, so we're doing really good here on time. We're just chopping things off the list. Let's talk about multiple pump configurations. Let's say that you want to model a whole bunch of pump curves with a single pump junction. You can do that. So I'm going to put a new pump on the workspace here, and then I'm going to open up a spreadsheet. Da-da-da. All right. Let's say you have a spreadsheet that you have a whole bunch of pump curves in. You hired an intern for the summertime or for their Christmas break. and they spent their time going through a whole bunch of different vendors' pump curves, adding them into the spreadsheet, and now you want to get them into Fathom. And so it's very easy to do this. So when I go into my pump junction here, when you click on enter curve data, there's two methods. There's simple method. This is one pump curve per pump. So you'd have to at least enter a pump curve for every pump on the model, which you could easily copy and paste the data, or you could import it from a CSV file. The other way is multiple. So for multiple, this is where you can create a whole family of curves. And they can be related or unrelated. It doesn't matter. They don't have to be the same vendor. You can do all sorts of different vendors, and they can be completely different and not match, and you can still do this. So I'm going to create, well, first of all, I'm going to delete the default one that's there. I'm going to create a new pump curve. So I'm going to do 1800 RPM, 8 inches in impeller size. Give it a description like model number 1. Now I'm going to go into my spreadsheet. Here's my data. So I'm going to select it and copy it. Go back into Fathom, and I'm going to paste it in. Generate my curve fit, and then update my configuration. So now I have one impeller trim that I can use. Let's do another one for 7 inches. So this will be model number 2. And I'm going to select the 7-inch impeller trim data, paste that into my table, and generate a curve fit. Now I have 2 configurations. I'm going to do 2 more. The third one is going to be a 3600 RPM pump, and it's going to be 4 inches impeller size. Now I'll start using letters, so this will be model A. This data is all the way at the bottom here. So there's my 3600 4-inch impeller trim pump data. Paste it in, generate the curve fit, and update the configuration. One more, 3600, 5 inches in diameter, model B. Go back to my spreadsheet. As you can see, this is very, very easy to do. Paste in the data, generate your curve fit, and update the configuration, and voila. So now I have a lot of flexibility. This is so cool because I can go into these drop-down menus and simply change to whichever pump curve I want by selecting from these drop-down menus here. And then I can also change my RPMs in the same fashion with its drop-down menus. And so when you do this, it will really streamline your process. So after I build this information in here for this pump, you can have 100 pump curves for one single pump junction in this fashion if you like. So I'm going to click OK, and then I could drop another pump on the workspace, and in this model I can copy the junction from, or the data from that previous junction, which is J19, and there it is. But there's a better way. The better way is to add this to your local user database so that you don't have to keep repeating yourself on additional models. So you would select that pump, go to database, and then add the component to the database. We'll call this pump for webinar. So now I can open up a whole brand new model where I have not done any definition, and then open up a pump, and then for my database list, choose pump from webinar, and bam, there it is. So this is awesome because you don't have to go in and keep redoing your work every single time. Do it once, add it to your database, and it's there for you to be able to use forever. Or until you delete it. So that's multiple pump configurations. All right, we are down to 2 more topics, so we're doing good. Let's talk about viscosity corrections. For that, I'm going to open up a whole separate model for this. So give me just a quick second here. All right. So here we have a system which uses a very high viscosity. The viscosity of this fluid is 500 centipoise. So your pump is going to be cranking really, really hard to pump this very viscous fluid over a hill. So the elevation at your pump is 720 feet. Your high point is at 1,250 feet. So that's 500, about 500 feet of elevation change that you're having to pump against. Your supply reservoir is at 750 feet, and that's your liquid head there. We do have a pump curve built in, and we don't have a MPSH or efficiency curve. We're just keeping it simple here. But we have two cases. We have one case where we're not accounting for viscosity corrections. So the pump is going to operate right on this curve, and you're going to see how the resulting flow rates and head rise values are actually over predicted. So it's very important to account for these correction factors. In my viscosity correction scenario, the way that you can easily account for viscosity corrections is on the optional tab by simply checking this box to use viscosity corrections. The AFT Fathom and AFT Impulse will use the Hydraulic Institute standards for correcting your pump performance due to high viscosities. You only need to do this if your system fluid is more viscous than test fluid. So if your viscosity is essentially more viscous than water, that's when you need to account for the viscosity correction. However, if you have a system fluid where the viscosity is it's less than the viscosity of water or whatever your test fluid is, you don't have to account for viscosity corrections in that case. There's two ways that you would account for the viscosity corrections. One way is by either assuming that your flow rate is at the best efficiency point. That means in my pump model, I do not have any efficiency data entered in. So whatever flow rate is calculated for this system here, I'm assuming that that flow rate is going to be my best efficiency point flow rate for the pump. So it's an approximation. If you want to have something more accurate, then you would choose base correction on flow data at the best efficiency point. You can either enter an efficiency curve for that, or if you know what your best efficiency point flow rate is, you can enter that directly. And then you would enter your rated speed for the pump, and then you can do the correction calculations. Here, I'm going to assume that the calculated flow is at BEP. I'm going to do a quick batch run and run both of those scenarios sequentially with each other, and we're going to compare the results side by side. All right, perfect. So I'm going to load my scenario, go to the output window. I'm going to look at both scenarios at the same time. And we just care about what's going on with the pump right now. So as you can see here with the results, if you do not account for viscosity corrections, your pump flow rate is 151,000 barrels per day, and your pump head is about 1,620 feet. So that's without accounting for any viscosity corrections at all. However, if you account for viscosity corrections, you can see that your actual resulting flow rate is much, much less. And so you're not getting as much flow rate there. And then when you account for the viscosity corrections in that way, you can scroll over to the right, and these are the correction factors for your pump. This is your correction to efficiency, correction to the head, and then correction to your flow rate. So as you can see, your efficiency is dropping by about 28%. So your pump is going to be 28% less efficient. Your head and flow rate, they're dropping by 7%. And so you've got 7% less flow and head available than you actually thought you had with the pump curve. And so this just goes to show when you're running your system and you're sizing your pumps, you want to make sure that you have a pump that can deliver this much more head and flow rate, that way you count for those corrections in a proper fashion. All right, we're doing really good here. One more topic. The last topic is energy cost calculations. So let me go ahead and open up a separate model for that here. Go to my desktop. Let's see. All right. So we got this, and then I'm going to open up another spreadsheet here. All right. Okay, so here we have two systems on the same workspace, and this the system on the left-hand side, this system operates the pumps at 100% speed, and I'm using my flow control valves to control 1,500 gallons per minute through each heat exchanger. So my total flow through the system is 3,000 gallons per minute. So I'm using my flow control valves here. On the system on the right, I have failed open my control valves like they're not even there, because on each of the pumps, I'm using a VFD with a control set point. So instead of using control valves, each pump is going to operate at 1,000 gallons per minute. That gives me my 3,000 GPM total, and I'm going to calculate what my costs are for half a year. So my peak flow rate is 3,000 gallons per minute, 12 hours a day, 365 days a year. My energy cost is 10 cents per kilowatt hour, and that's how I get my 4,380 hours. So when I go and run the model, I just turn on the cost calculations, and I can do a cost comparison very easily. So the cost report shows that the three pumps operating at 100% speed are spitting out about $191,000 each to run each of those pumps. Versus with VFDs, it drops them down to $186,000. So there's a decent amount of savings there. Now let's take a look at the actual operation. Your operation for your pump, you are getting exactly 1,000 gallons per minute through each pump. However, in the system on the right-hand side, your pumps need to drop by just over 1% speed in order to give you the desired flow rate. Here's your flow through the heat exchangers. When I use flow control valves, you are getting exactly 1,500 gallons per minute through each heat exchanger, versus with a VFD, you're still getting very close to 1,500 GPM. If you look at the valve summary tab, you can see from the system using the flow control valves, each of those flow control valves are having to take out a significant amount of pressure for you. So this is wasting a whole bunch of energy. It's like driving your car with your foot on the gas pedal and the brake pad at the same time. So you've got 27 pounds of pressure loss in one valve, 16 pounds of pressure loss in the other. Here's the cost summary for the peak hours. You have, if you go through and sum up the total costs, by using VFDs, you're saving just over $15,000 a year. So that's pretty good. Maybe it's not enough that you actually care about, but it depends on how big your system is. However, I have my off-peak situation. My off-peak hours, instead of delivering 3,000 gallons per minute through the system and 1,500 through each heat exchanger, I'm delivering 1,000 gallons per minute through each heat exchanger. And so the off-peak hours, the pumps were not originally designed for this operating case. And so you're going to see how this clearly wastes a lot more money and energy. So again, each control valve here on the left is operating at 1,000 gallons per minute. Pumps are at 100% speed. Right-hand side of the system, control valves are failed open. Each pump is operating at 667 gallons per minute to give me 1,000 GPM through each heat exchanger. And my off-peak hours are going to be 12 hours a day, 365 days a year for off-peaks. That's the same time frame. So now when I go to run my model here, when you go to look at the cost report, you can immediately see that the cost savings are much, much more significant. Then for your pump summary, in order to get the same exact flow rate through each system, instead of bearing out your pumps at 100% speed, you can drop them down to 67% speed. And look at this. They're still operating very close to their best efficiency point. So not only are you saving tons of energy and tons of money, your system is going to be a lot more reliable and it's going to last longer because you're not going to have a lot of vibrational problems at your pump. If you look at your heat exchanger summary, here's your flow rates through each heat exchanger, so right at 1,000 gallons per minute, which is what you need. And then your flow control valves, man, look at this. To get that lower flow rate, your control valves are having to crack down about 570 psi. So to get that lower flow rate, your control valves are just barely open, and that's just really wasting so much energy. So when we total up all the costs here, your off-peak hours alone, $326,000 a year in energy savings. And this is for a very simple system that I made up. There's nothing really huge or special about it. Imagine what you can save in your own plant and for a system that's actually real. The total yearly savings, $341,000 a year. And so that's how you can do a very quick energy cost calculation for seeing where your pumps are going to be costing you over time. All right, so we are now officially done with each of these topics. There's a lot of additional resources that you can access on our website, which will help you learn more about our software. So if you go to aft.com, we've got our Learning Center here. We do have excellent training seminars at our facility in Colorado Springs that we teach 3 times a year. So we do have our training seminar schedule posted for 2018, and so you can find that information right here, and you can register right off our website. We've got tons of case studies for our software that you can go through, technical papers, white papers. We've got a whole bunch of tips and tricks articles that you can look through, video tutorials, and of course our additional webinars. So in the next few weeks, we'll be posting webinars for 2018. So stay tuned for those, and you'll be able to register for our 2018 webinars. We've got a lot of good stuff planned for you guys. It looks like I did have a couple of questions here, and let's see. Yes, as mentioned, I did record the webinar, and so you will receive a link. I'm not going to send it to you personally myself because you're going to get that link to the webinar automatically. And so just keep your eye out for it, and you'll get it. And anyway, thank you all very much for your time today. I really appreciate your attention, and I hope that you learned a lot of ways to make your pump modeling a lot more efficient and effective for your systems. If you have any additional questions for tech support, email us at support@aft.com. For any sales questions, you can contact us at sales@aft.com. Thank you very much, everyone. Have a wonderful Christmas and New Year's, and enjoy the whole holiday season. And if you're in a very cold area, stay warm. If you're in a very hot area, stay cool. Take care, everybody, and have a great day.